Hello, everyone. I'm going to talk today about linear models for regression. I'll try my best to finish the topic. Let's see. I'm going to share my screen. So let me also talk about the bootcamp, that mini bootcamp that we are having. On Saturdays, Pacific time, between 9 and 11. So 9, 11 Pacific daytime, Saturdays. We are having the next 4 weeks. We started this week, actually, this past week. I don't know, some of you guys might have already joined into the first class. We are having a mini boot camp. We start from very basics. You don't have to know too much about machine learning. If you are only just familiar with Python, that will be enough. I'll try my best. I'm trying to do, keep it very simple at very basics, and then try my best to answer all the questions. So I think if you are a beginner, you might benefit from that mini bootcamp. Today, actually, I'm just going to jump ahead from that mini bootcamp. In the mini bootcamp, we just started last week. We started from how we can load data to the platform and then work on the data set, just the introductory exploration of data set. And then I'm going to keep talking about that. And then mostly we're going to spend some time on pre-processing data set. Once you have the data and then you pre-process data, your target is preparing the data to train it using some machine learning algorithm. So I said I'm jumping ahead. So let's say you pre-processed your data, and then you are ready to train your data for some machine learning algorithm. That algorithm, in this case, we are going to use regression. And you can ask your questions anytime. I'll try again my best to answer the questions. Yeah, we post the recordings of the mini bootcamp and any kind of workshop at Magnimind. Okay, so I don't know if it is posted yet, but we normally post all the recordings of the mini bootcamps. All right, so I'm gonna follow the same way that we did last time. I'm going to spend some time on introducing the concepts, and then the second part, I'm going to go through an exercise with you guys step by step. So for that, you can use your Jupyter Notebook, and if you don't worry, you can use, if you have Gmail account, you can use Google Colab. I'm going to share the content with you in a moment. Let me see if I can share it now. Yeah, so you can download the material from here, okay? So for today. Okay, so let's get started. Linear models for regression is one of the simplest model that you can think of for any machine learning project, because it is simple, because everybody thinks we know about linear regression. It might be overlooked. It might be, we might be arrogant not to use it. So forgive me if I'm using the word incorrectly. But actually, linear regression might work miraculously well for most of the data sets if you have enough number of data points. So I think if you are going to be a data scientist, or if you want to pursue the data science as a career, you have to be very comfortable in training your data, at least for two kinds of models. One is some model that is going to be taking your target variable at the continuous target variable, and another model that is going to be predicting a discrete target variable. Again, if you remember from last time, so when I say continuous, I'm referring to a target variable that is taking values from a large set of values. Like in this case, for this class, we're gonna be using house data set and then house price data set. Our target variable is house price. We are trying to predict house prices, and house price can take values from a wide range of values, right? It's a continuous variable. So for predicting house prices, well, you can use linear regression, you can use random forest, you can use super vector machines, you can use neural networks, you can use deep learning models, okay? So you can use a lot of different models. But what I'm saying is you need to be very comfortable with using at least one model. In other words, you need to come up with a model that is working, that is predicting reasonably. And I think that is the very first step that you should take to become a data scientist. So again, if your target variable is taking discrete values like yes, no, spam, not spam, 1, 0, right? Then you need to know a classification algorithm, and you should be very comfortable. Again, you can simply start from logistic regression, right? So you must be very comfortable with training your data if your target variable is a discrete variable, training your data on a classification algorithm. Okay, yeah. So I don't know how to change the settings for saving the chat, but if we cannot do it this time, maybe we can do it next time. So I really don't know how to change the settings. All of us, I'm pretty sure, learned about linear lines, right, in middle school and high school, and the linear lines have this y-intercept and x-intercept and this slope, right? So when you have a linear line like this, so right, so this is the line, and this line has some equation like mx plus n, and n is going to be this y-intercept, and m is going to be the slope of this line, right? So what we are going to try to do with linear regression is we are going to try to find an equation for a line. So in this case on the screen, I just draw a line that you can see on a 2D plane, right? So there is this x and there is this y axis. So in most of the time, our data set is not going to have only 2 dimensions. It's going to have multiple dimensions. So I'm just drawing this line to depict how it would like to form a linear line for your data set. If your data set is composed of only one feature, here x is feature. Again, because we already learned about features and target variables in our previous class, I'm trying to not get into details of that. And then you have this target variable. Again, you might have multiple features. Here, I'm just trying to keep it simple and then have only a single feature. So our job is, if you had a chance to, create a scatter plot of your data set. Let's say your data is, again, composed of a single feature. Let's say you are using this house data set, and then your data set has all these nice features. One of the features is, let's say, room number of rooms, right? So another can be crime rate in the zip code. Another can be some socioeconomic indicators for that zip code, right? So these are features of your data set, and at the end of the features, you're going to have the target variable. In this case, let's say it's going to be the price, right? So again, let's disregard all the other features and just focus on room and price, and then you have data set for different houses. This is house 1, this is house 2, so on and so forth. So house 1 has, let's say, 3 rooms, and then it has a price of, I don't know, I live in the Bay Area, so a 3-room house in the Bay Area, don't be surprised, let's say it is $1 million, okay? And it's a cheap house, all right? And then there is another house with 2 bedrooms, and then this is an apartment maybe, and then it is, I don't know, 700K. Okay, so you put the numbers here. These are the prices. And then if you had a chance to create a scatter plot of your data set, again, just room and price, what you're going to see is, this is room, and this is price. What you're going to see is you're going to be, let's say, number of rooms is 3, and then house price, this is, let's say, 1 million. And then this is 700K. So you're going to just locating your data points on this 2-dimensional figure, right? And then again, this is 2. So if you had a chance to, plot all your data points on, put all your data points on this graph, then you're going to see these dots. Each of these dots is actually representing one data point. Again, these data points at this point they have only one feature, which is room, And the target variable, the dependent variable, is the price. And we are creating a scatter plot of room versus price, right? So we have all these different data points, which we are able to plot, okay? So our job is trying to find a line like this, that will go through these data points. But this line is going to be a special line. I can draw so many different lines that will go through these data points, but I'm looking for a line that is going to be among many lines which they are going through these data points. I'm looking for a line that is going to have the minimum distance, the summation of distance between that line and these data points, that will be minimum. The minimum sum of distances between the line itself and all the data points. All right. So again, I can draw so many lines going through these data points, but I'm looking for a special line that is going through these data points. And when I measure the distance between these data points and the line, the summation of that distance will be minimum. So what does that mean? What is distance? Again, this figure looks much better than what I drew. So let's look at this figure here. Again, imagine that one is room numbers, the other one is price. So when I say distance, I'm referring to, again, this is my line. Let's say this is the special line that I'm looking for, the green line. And when I say distance, I'm referring to the distance between a data point and this line. So this is the distance. This is the distance. What does that mean? Well, I mean, what does that mean? What is this distance? So let's say this is, again, room number. And this is price. Okay. So I'm going up to this data point. All right. I'm going up to this data point. And then I am going to cut this y-axis for this data point. Okay. So this is for this data point. Let's call this x1. Now the d1. This is x1. This is y1. So y1 is the price or the target variable value for data point d1. That is the true, I'm using the word true target variable value for d1. All right. So when I say distance, when I draw the line, again, for the same data point with room numbers x1, okay, if I were to predict the target variable value for a data point with x1 number of rooms, again, what I was supposed to do, okay, is I'm going to go all the way up, but this time I'm going to cut the line, okay? And then from that, I'm going to go towards the y-axis, and this will be my y1 hat. So y1 hat will be my prediction for the price for a house with x1 number of rooms. What is y1? Y1 is the true price that I know for a house with x1 number of rooms. Again, my data is about house prices. All right. So the distance between the line and the data point itself, this distance is actually the distance between my prediction and the true label value. My prediction, which is y hat, and then true label value, which is y. Okay, let's call it y1 hat and y1. So I'm trying to come up with a line which is going to minimize the difference between the prediction and the true label value for all my data points. So I'm going to find this for the first data point. I'll do the same thing for the second data point and the third data point, so on and so forth. Let's say I have n data points. So I'm looking for a line that is going to give me, if I sum up all these data points, right, all these differences, that is going to give me the minimum distance, sum of the distances for all these data points. And again, because sometimes this difference will be positive, sometimes it's going to be negative. I don't want positives and negatives cancel each other because that will defeat the purpose of finding the best line. So that's why I'm going to just take the square root of these differences. Again, this is the basic idea actually behind finding a line that is going to minimize we call this error. Okay, error. Error is the difference between the predicted value and the true label value. Okay, mathematically, how can I show that? Mathematically, what I can show is, sorry for this. Oh, working. Okay. I'm just checking if we have any questions. So again, if you are already familiar with linear regression so far, it may be very simple, but anyone who's new into this, please feel free to ask any questions. I'll try my best to answer the questions. Your data set may not have a single feature. It might have multiple features, and most of the time that is the case. You're going to have a data set with multiple features. Again, remember, data sets, the features are represented by capital X in general, and then we are using small y for the target variable value. Capital X will be composed of so many vectors, as many as the number of your features, let's say x1 to xp, and you're going to have a single vector which is corresponding to your target variable, right? So our goal is coming up with this line. In this case, our line is very simple. We only have a single, feature. So our line is actually y equals w1 x1 plus b, right? For a single feature. So this is our feature, right? And this, I said from middle school, remember this was the slope. This is actually the coefficient corresponding to the feature x1, coefficient corresponding to the feature x1. So our goal is finding this coefficient, estimating this coefficient, so that for a given x1, my prediction is going to be for a given x1, this is going to be my prediction. W1 times some x1, let's call it x1 plus b. So this is going to be my prediction. But the true value for x1 is going to be actually y1, right? This is the true value for x1. What I'm going to do is I'm going to find a y hat, y1 hat, which is going to be as close as possible to y1. To find that y1 hat, I need to estimate the value for this w1, which is the coefficient of x1. In other words, how important, right? How important x1 is for predicting y1. Okay, w1 is going to indicate how important x1 is when we want to predict y1. So if x1 is not relevant in predicting y1, you expect w1 be 0. And by the way, when I say how important, don't mix this with the magnitude of w1. So if x1 is a really big number, right? If x1 is some feature that takes really big numbers, then w1 can be a really small coefficient because you're multiplying x1 by w1, right? But if x1 is really irrelevant, w1 is going to be 0. In other words, you're not going to even consider x1 for your predictive model. And this b is going to be the bias term. What does that mean, bias term? What does that mean? So think of this line here, this green line. So what you can do is, by changing b, you can shift it up and down. Okay, I mean up and down. By changing b, the line can shift up and down. So b is referring to this actually, this y-intercept. If b is high, so the line is going to be going up. If b is low, the line is going down. So by changing b, you're offsetting the line. Okay, you're offsetting the line. Okay, and w1 is again the coefficient for x1. If you have multiple x's like x1, x2, xp, that means you have multiple features, then you're going to have a w for each feature. So in other words, your prediction y hat is going to be w1 x1, this time plus w2 x2 plus blah blah. How many x's you have plus wp xp, right? And then plus b. That b is the bias term. So our job is estimating these w's. These w's are going to give us the model that will help us make prediction for a data point with feature values x1, x2, blah, blah, xp. Right? So you can write it in this format, or what you can do is you can make this, turn this into a vector, and you can take only W's, okay, and then put them into a vector. So what's gonna happen is W1, W2, and WP. This is gonna be a vector. And then taking the transpose means you are turning this vector into this format, W1, W2, WP, okay? And then you do the same thing for X1 and X2, again, X1, X2, XP. So this is the vector, which is representing the feature values for a single data point, all right? And then this means the following. Again, I'm using W transpose X. This means the following. So what you're doing is you are taking W, W1, W2, WP, and then again, remember X is a column vector, X1, X2, XP. So you are just simply multiplying these two vectors, right? So it means W1 times X1, and then W2 times X2. Of course, there is plus, and then W2 times XP. So that's why we have this W transpose times X. It is simply representing this summation here, okay? And then you have this B. Well, if you like, what you can do is you can add one. You can add one at the beginning of this W vector, and then add B here at the beginning of your feature vector. So this way you can even get rid of B, right? And then simply write Y hat is W transpose times X. Okay, so this is a very simple introduction, mathematical introduction to how we can, show the summation of features and then coefficients in a predictive model. Again, mathematically, if you want to show how you can find the difference between your predictions and true values, what you're going to do is, again, remember, W transpose X is actually nothing but your prediction, okay? So what you're trying to do is you're trying to find the difference between your prediction and the true labor value. In other words, Y hat minus Y, okay? So this is what we were trying to do in the previous slide. And I'm going to take the squared of this for each data point. I is representing each data point. And then I'm going to sum this up across all data points. Right? So this is representing the total sum of the difference between my prediction and the true labor value. Okay, the total sum of the prediction between the true value, the total sum of the difference between the prediction and the true value. Of course, don't forget this squared term. So most of the time, in general, in machine learning, we call this loss. Okay, we call this loss in general in machine learning. For linear regression, I mean, we call this difference as residual. Right? Residual is the difference between the predicted value and the true labor value. All right. Just 1 second. Somehow it stopped working. Just 1 second. Sorry about that. Okay, it came back. Sorry about that. We can see it, right? Can you see it? Okay. All right. So, yeah, in a second, I will stress. So this is called, what I just tried to describe is called ordinary least squares. Ordinary least squares. In other words, OLS. Okay, ordinary least squares. Again, when I say ordinary least squares, if someone says OLS, all we are trying to do is we take the prediction, y hat, which is nothing but W transpose times X. We subtract the true label value, which is nothing but Y. And then we are doing this for all individual data points, taking the squared, summing them up across all data points if you have n number of data points. Okay, and then you are trying to minimize this. Okay, this is how you are going to estimate the coefficients for an ordinary least squares. Let me ask you the question. You have data points D1, D2, D capital N. Let's say you have n capital N number of data points. When you estimate W's, let's say each data point has X1 to XP features. When you estimate W1, W2, WP. Question, do you think these W's are the same for all data points, or are you going to estimate a different set of W's for each data point? So let me put it this way. So is it the same W's? Please say yes or no. Okay, you can type yes or no. Okay, so we have yes and no. So we have yeses and nos. All right, guys. So we have, again, n number of data points, capital N number of data points. For some data sets, you have 1,000 data points. For some, you're gonna have 1 million data points. Your goal is estimating these W's so that you can get that line, right? Which is gonna go through those data points. Now imagine, let's go back to that simple two-dimensional picture, price, room, price. Again, remember we have multiple data points here. And we drew a line, right? Remember, we drew a line, and we said this line is y equals W times room plus B. So room is, for each data point, it has a different, there is a different room number for each data point. Y is price. For each house, we have a different price. But for all the data points, we have the same W, we have the same B. So there is a single B in here, right? There is a single Y intercept. We don't have multiple intercepts. And there is going to be a single W value. So this will be the same when you move from a single feature into a multi-feature data set, okay, multivariate data set. Again, you might have n number of data points. Can be 1,000, can be 1 million data points. Your goal is estimating the set of W's that will give you the best line going through these data points. And that line will have a single, just one W vector, okay? So in other words, this W vector will be the same for all data points. You're not gonna have a different W for a different data point. It's gonna be the same for all data points. That's why your prediction is gonna be different. So you're gonna have a difference between, so that's why you have these differences. Because this W is about, I'm using the word average, but not, this may not be exactly true, but this line is about the reducing the average error between this line and all your data points. So that's why we have a single W. Just setting a single set of vector of W's you are going to make predictions. That is the power of regression, right? So once you can find this P number of W's, you can make prediction for any data point after dn. If you have dn plus 1, dn plus 2, if you have 1 million more data points, your W's are going to be a single set of W's, and then you're going to be able to make predictions for these 1 million extra data points. Okay, so this kind of models, we call them parametric models. Why? Because what we are trying to do is for n number of data points, we are trying to estimate one set of parameter values, right? And that is going to simplify things for new data points. You're just going to take that data point and then multiply them with these W's that you have already estimated. Okay, I hope this part is clear. Now, there is one topic that should be explained before we begin to talk about linear regression, but I assume that some of us may not heard about it or have read about it. That is called model complexity. Okay, so anyone who ever heard about overfitting, underfitting? That is some very basic interview question. Overfitting, underfitting. What does that mean? Yeah, Kautar, your questions. If we change the training data, the vector W can change? Yes, of course. When you change the training data, the vector W is going to change. So when you retrain the model, you're going to have a different set of W's. Means my t-shirt is too large or too small for me to wear. Okay. Over the model that is biased too much by training data, that is also correct. Yes. So what Milan gave the description, t-shirt is too large or too small for me to wear, is underfitting. Okay. So if it is too small or too large, underfitting and overfitting. Underfitting actually. When it is overfitting, what happens is, I'm going with the example of t-shirts. What happens is the t-shirt producer, manufacturer, is going to manufacture t-shirt for each person individually. That is overfitting, right? Imagine a factory which is manufacturing t-shirts for each individual. Let's say the manufacturer took in 1,000 people, and then it only manufactures t-shirts for these 1,000 people, only follow the perfectly matching to them, right? So those manufactured t-shirt that is perfectly matching to these 1,000 people, specially produced for them, is actually overfitting. Because if you take those same t-shirts and then try to sell people outside of that group, those t-shirts may not be fitting to the general population. Okay, so that is overfitting. Underfitting is what you do is you're just going to produce only medium-sized t-shirts. Okay, so but we know that in the population we have small, we have large size, we have X large, right, or XXX large. So if you simply just simplify things too much and decide to produce only medium-sized t-shirt, it's very simple. I only produce one size of t-shirt, which is medium. So that will be underfitting. So you still have a chance to cover a larger portion of the population in terms of satisfying their need for a t-shirt, right? So I know that there are large, and then there are X large, and then there are medium and small sizes, but I only choose to produce medium size because it makes things simpler for me. But then it makes things difficult for people who are going to wear those t-shirts, right? So only producing medium size, but disregarding anything other than medium, it is called underfitting. Okay, so I just used the example that Milan gave us. So that is overfitting and underfitting. Our goal as data scientists is coming up with models, okay, which are not overfitting or which are not underfitting. The models that would represent as good possible as good as possible. So representing the trained data set, but as general as possible to be fitting to the general population. So that's why these t-shirt companies came up with sizes. So medium size and large size and X large. So that they can cover the entire population, but they're not going to be perfectly fitting. But people will be happy. So more or less. So I know that a large t-shirt is not going to fit me perfectly, but I'll be happy with that. So the difference between my body size and then that t-shirt is that error. Okay, that error that we mentioned, y hat minus y. Anyways, so let me stop talking about t-shirt. So model complexity is, okay, how detailed your model is going to be representing your training data set. Okay, how closely your model is going to follow your training data set. Again, remember, you need to train your model. To train your model, you take your data and then you split that data into train and test. Okay, so you're going to train your data based on what you have in your training data set, and then you're going to test this data set, test your model on a test data set. Please come to the Saturday sessions to learn more about this train, test, split, and everything. All right, so my job is train my model on the train data set, but my model, I mean, yeah, should be fitting to my train data set, but in my mind, I know that I'm going to have new data points coming. I know that there are more data points outside this train data set. There are data points all over the place. Okay, I only have a small portion of what data available in the universe. Okay, so my goal is train a model which is going to be representing my training data set, but then it will also be general enough to fit to data which is outside the training data set. Okay, that is my goal. This is the sweet spot that people talk about. So not too overfitting to your trained data set, the model, not should be underfitting to your trained data set, a model that is fitting your trained data set, which will give you enough accuracy on the trained data set, but it will be the most generalized model that can be used for any data point outside your trained data set. Okay, so if you increase your model complexity, you might, let's say, if these lines are representing the model accuracy, okay, if you increase your model complexity, what's going to happen is your training, the model is going to be, after a while, maybe fitting perfectly to your trained data set. So what does that mean? Fitting perfectly, what does that mean? Remember, this is prediction, and this is true label value. Let's say I give you 100 data points, D1, D2, D100. You divided these data points into two groups. Let's say D1, D2, D80 are in the trained data set, D81 and D100 are in the test data set. So this is trained data set. Now, you trained and trained and trained a model. In other words, in this case, you're trying to find a set of W's, okay? And for linear regression, that will be really impossible to come up with some model that's going to give you zero error. But let's say you have this perfect line, which is going through these data points, okay? And then using that line, you begin to predict for your training data points. Again, this is Y1, this is Y2, this is Y3, and this is Y80. And this is your true data points, Y2. Again, I'm talking about your trained data set, and then you have 80 data points, and you created a line, a special line that is going through these data points, and then actually that line is not a smooth line like this. It's a non-linear line. It's a non-linear line which is making all kinds of curves. Actually, what the line that I'm talking about is actually a line that is going through each and every 80 data points. So this is how the data point is going to look like. This is what I'm talking about. I'm talking about the data line which is going through all your data points. Can you create such a line? I mean, may not be always possible, but for some data sets, for smaller training data sets, it is possible. You can create a you can create a line which is going through all your data points. So what's happening here is my line is exactly going through the data points. In other words, if I subtract my predictions from true label values, will be zero. Will be zero. What does that mean? I created a model which is perfectly fitting to my trained data set. In other words, my training accuracy is, in this case, 100%, or my R squared, I'm talking about linear regression, my R squared is 1. Right? But if you take this model and then use it outside, so the new data point arrives, a new data point might fall here. Another new data point might fall here. Then what's happening is, between these new data points, which are coming from outside, these are called test data points, you're going to have these errors here. As you said, this perfectly fitting model, which is perfectly fitting to your trained data set, is not fitting to your test data set. Okay, those t-shirts that you produced, manufactured, which are perfectly fitting to those 1,000 people, let me reduce this 100 people. Right? When you try to sell exact copies of these t-shirts outside for other people, if these, and then the worst is those 100 people are slim size t-shirt wearing people, right? Those t-shirts perfectly matching to this 100 people will not be matching to people outside the factory. All right. So our goal is finding a model which is going to give us a reasonable accuracy on the trained data set and the maximum accuracy on the test data set. That is a sweet spot. Okay, sorry for making this too long. Let me go back to my linear regression model. All right. So my linear regression model, remember, this was my linear regression model. My linear regression, my goal is trying to estimate W's, which will minimize the distance between the predicted value and true value for across all my data points. And remember, I called this as loss. So we're going to use the word loss and that our goal in training any machine learning algorithm later on, whatever algorithm you learn, your goal is reducing this loss. Okay. Okay. Now, what happens is, if you just focus on reducing the loss for your training data points, by the way, you don't have any other chance, right? So you have the training data points to train your model. So this is what you have, your training data points. Your model, you're going to shape your model. You're going to estimate your W's using this training data set, right? So if you make your model fit perfectly to this training data set, in other words, fitting perfectly means you are going to make this loss closer to zero for your train set. What will happen eventually is your model will be nicely trained on this trained data set, and your loss on the trained data set is reduced, let's say almost zero, but then you will have a model which is perfectly fitting to this trained data set, but not fitting to new data points. In other words, you're going to have an overfitting model. You're going to have an overfitting model that is not working properly for new data points outside the training data set. All right. Then what are we going to do? How can we fix this problem? So remember, I started with talking that we are looking for a line which is going through these data points, and this line should be a special line that will have the distance between each and every data point, the summation of those distances will be minimized. So that is what's happening here in this part. But then I suddenly began to talk about overfitting. I said, yeah, this line might be the best line for these data points, but be careful. Maybe there is another line which is not the best for these training data points, but that line might be the best for other data points outside your training data points. Okay, so on purpose, okay, on purpose, what we're gonna do is we are going to reduce the predictive power of our model for this training data set. We are going to somehow make this perfect model imperfect for the trained data set. Why? So that this model can be more general, okay, for new data points outside the trained data set. All right. So how are we going to do that? How are we going to do that? What we're going to do is we are going to introduce this second part. Okay, and this second part in most machine learning books, if you check, it is called penalty. Okay, why do I call it penalty? I'm penalizing my model for being too perfect. I'm penalizing my model for being too perfect. So how am I penalizing my model? What does that mean? So let's go back to this this loss here. Okay. So what's happening here is I'm trying to estimate some W's that when I multiply by xi's and then add up W1, X1, W2, X2, and subtract this summation from yi, and I do this for all the data points across n data points, sum them up, this loss should be minimized. So, okay, what is happening here is, for big values of W's, now I'm adding loss plus penalty. Now I'm talking about loss plus penalty. This minimization is working for both loss and penalty. So what happens here is, for big values of W's, I'm going to incur a higher penalty. And let's think about this. Well, what does that mean? Why big values of W's are so, disturbing for us, right? Why are we trying to minimize? And then Miles said something, I think of over there as when you are fitting to the noise, not signal. Yeah, that is also correct. So in any data set you have also noise coming with the data set. And then the model perfectly fitting to your trained data set will actually fit itself to noise as well. So any data set comes with signal plus noise, and then you may not separate signal and noise from each other. So when you train your model perfectly fitting your trained data set, the model is actually fitting itself to this noise as well. So for big values of W, so imagine that W is some number. So if W is 0.1, then W squared would be 0.01. If W is, let's say this W1, this W2 is 10, W2 squared would be 100. In other words, as W increases, the impact of those big W's will be significant on my minimization problem. So remember, I'm trying to minimize the overall loss. Overall loss here is loss plus penalty. Okay, guys, what I'm trying to do here is I have these W's. If I leave them free, if I leave my W's free and then ask them, do whatever you want so that you can minimize the distance between predictions and true labels in my trained data set, do whatever you want. If I tell this, do whatever you want, some of the W's are going to take the liberty, to go really up to very high numbers. Why? Because when W's go to those high numbers, you are going to have the minimum distance between the predictions and true label values. So that W's are going to search for all the values that any chance that is going to minimize this loss. And sometimes they're going to go all the way up, and then sometimes they're going to go all the way down in negative. So when W's are really big in magnitude, what happens is when a new data point comes, so this guy was never included in your trained data set, and this guy has this X1, X2, and XP, right? So this X1 and XP in the trained data set took some extreme values. Why? Because the goal is minimizing the loss for the trained data set. And when you are minimizing that, you let W's take any value they want. And somehow W2 took a really high value and WP took a really low value. So when a new guy comes with his own feature values, and then I don't know this guy's Y value, I don't know the true label value for this guy. I just need to make a prediction for this guy, okay? And what's gonna happen is this X1 is gonna multiply it by W1, and this XP will be multiplied by WP, because W1 and WP are taking really extreme values. This multiplication is going to give me a Y hat that might be really different than what the true label value for this guy, this new guy. Why? Because somehow W1 and WP, the values of W1 and WP came out to be really extreme values because the model was trying its best to fit itself to the training data set. And this is a new guy which was never in the training data set before. So I specifically penalize W's that are going to these extreme values in positive and negative direction. So I want my W's be in, by penalizing them, if anything going up, I'm just hitting it. So it comes back to an acceptable level. So that, yeah, I accept some error that I will have for my training data set, but then I'm not going to have this huge difference between the true label value and predicted values for my new test data points. Okay, so that is the logic behind introducing these penalty terms. And we have two main models that we can talk about when it comes to linear regression: ridge regression and lasso regression. When I say ridge regression, I am adding this penalty term alpha times W squared. And this alpha is, I'm controlling that alpha. It's a hyperparameter. Hyperparameter is a parameter that you have to adjust its value to, maximize the predictive power of a model and then make it as general as possible for new data points. Okay, so you have to tune up your model for your hyperparameters, and alpha is a hyperparameter in this case. So for ridge regression, the penalty term comes in terms of the squared sum of the squared W's. So, or we call this L2 norm. What is L2 norm? L2 norm is W1 squared, W2 squared, WP squared. Okay, L2 norm. All right. So that is, are you increasing the penalty for large W's to guard against outliers? That is correct. So sometimes if you have outliers in your data set, that they are going to have an impact on your W's. That is also correct. Yeah. So this is the general format for your machine learning algorithms. If you study any machine learning algorithm, deep learning models, this is the main loss function that we talked about, and that you can change this function depending on what type of model you have: linear regression, logistic regression, I don't know, some CNN, RNN, whatever you have. And this is the penalty term, okay? And alpha is the hyperparameter. So if alpha is 0, penalty term will be, you're not going to introduce any. In other words, your model has the danger of overfitting. All right, I will stop in a minute. Okay, I'll give you 5 minutes break before. I'm going to go through this code with you when we do exercise together. So that's why I'm skipping this part. How do you measure the performance of your model? Okay, so you take the data, you clean the data, you train model on data, okay, and then you evaluate your model. By the way, there is a cycle between training the model and evaluating the model, right? So if you're not happy with the model, you go back and retrain the model, make some changes in the model, and evaluate again. So evaluating the model is really important, guys. So how do you evaluate a linear regression model? To evaluate a model, you need to come up with metrics. Okay, you need to come up with metrics. What metric you want to use to evaluate your model? So it's very important. How can I compare the performance of my model with the previous model? So I need to have some metric to compare, right? So sometimes you can come up with some model that you don't have any metric, and it becomes impossible to compare it. So for linear regression, we have multiple metrics. Good news is we have multiple metrics. But we don't have perfect metrics. We have multiple metrics, and that's why when we compare, we use these. We don't use a single metric. We use multiple metrics because we don't believe each one of them is working perfectly. So one of the most common metrics that you might see in the literature when you look at any machine learning book is R squared. Okay, so from econometrics, you might have seen R squared too. So what is R squared? What kind of a metric is that? So for machine learning, linear regression models, so there are also different, slightly different definitions of R squared, and depending on how you define R squared, people will say, oh, R squared cannot take negative values. Some say, oh, no, R squared can take negative values. That all goes back to how we define R squared. Okay, so let's see what R squared means in our case. Okay. Now, if you look at here, you already know what this guy means. This is your prediction. Okay, whatever the model you created, y hat is the prediction comes out of that model. So this y bar, this guy, is average here. So let's say you are predicting house price. Y hat is going to be the average house price. All right. So what's happening here? What's happening here is in your data set, let's say you have n number of data points. Okay. You have n number of data points, and then you train some model. You trained model M1. That is your model. You call it M1. You just have a code name for that model, M1. So using this M1 for this n number of data points, you find your predictions. Like going back to the picture, remember, you have the line for each data point. You're first cutting the line and then going towards the y-axis and then see where you cut the y-axis. That is your prediction, y hat. So for each n number of data points, you have your predictions. And then what you do is, for this n number of data points, you find the average. You simply take the average of this n data points. Okay. So if someone comes to you and says, can you come up with a model that would predict house price for a zip code? Okay, for a zip code. So what you can do is, the simplest approach, right, is I take all the house price in that zip code, take the average, and then my prediction is the average. So any house in that zip code, what is the price? The average price. That is y bar. This is the simplest model. Okay, so here in the denominator, I'm taking the difference between this average and my true label values. In other words, why this guy is true label. This is also true label value. In other words, these are the true prices for the houses that I know of. Y bar is the average of the house prices, again, let's say in that zip code. So here I'm taking the difference between the average and true label value. In other words, if my model was, the average, okay, if my model was a simple model that is giving me the a prediction for each house as the average house price. So that would be my total error or loss. If my model was simple, and then I'm simply using the average for prediction for any house in that zip code. And what is this? This is the loss for some other model. And let's say for model M1. So I took these predictions that I got from my model, and then I find the difference between true label value and then my model prediction. So what I'm trying to do is, here is this really simple model I have, okay, which is just simply giving me the average. And here is some model that I want to test, which is giving some predictions, okay? So if this loss for your model is greater than the loss for your simple model, which is only using the average value. If your loss for model M1 is greater than the loss that you would incur if you had used this average model, with simplest model. What does that mean? That means your model M1 that you spent time to train your model is actually working worse than simply using the average values. Why would you spend so much time on that? Why don't you simply use the average value, right? So by using R squared, at least, okay, I'm not giving you the theory bit, but R squared is actually if you look at the textbook, it's going to tell you that R squared is telling you how much the model is explaining the ratio of change in the data set. Okay, the variance in the data set. Yeah, that is exactly precisely what R squared is doing. But interpretation of R squared in terms of a machine learning predictive model is actually, if you use this as a metric, it just tells you how well your model is working with respect to using a simple model that only gives you the average value. So if this guy is greater than the denominator, that means your loss is greater for this so-called sophisticated model with respect to your simple average model. So in other words, if numerator is greater than denominator in this case, your R squared will be a negative number. So 1 minus a number which is greater than 1. A number greater than 1, right? So if numerator is greater than denominator, you have a number greater than 1, and 1 minus a number greater than 1 is negative. If your R squared is negative, that simply tells you in this case that your sophisticated model that you came up with is actually working worse than a simple average model. What does it mean if your R squared is 1? Okay, which is, again, if your R squared is 1, be very careful because most likely you are overfitting. You are overfitting your model. If R squared is 1, that means your numerator is 0. If R squared is 1, 1 minus 0, right? So that means your numerator is 0. What does that mean? That means that your predictions are exactly equal to the true label values, which is overfitting. So your goal is getting closer to R squared equals 1. But if your R squared is actually 1, I would go back and then introduce some. Where is it? I'm sorry, guys. Introduce some penalty term. Okay. Bring R squared a little bit down. All right. So that my training, my model on the trained data set is not overfitting. And then my R squared on the test data set is increasing. By the way, when I said R squared equals 1, R squared equals 1 on the trained data set. Okay. So let me give 5 minutes break. I think I went beyond the time that I should have used for the first session, but let me give 5 minutes break, and then when we come back, we are gonna work on the code together. Okay. All right. Just see you in 5 minutes. Yeah, the material is in this folder, so you can get the material from the folder I just shared in the chat. Now I'm going to just do a small exercise on linear regression. It's just a very simple coding, but you will see that coding part is simple, okay? But whichever model you're gonna be working, okay, as you continue on data science, whatever model you are working, please try to understand what is happening. The coding part, I will say most of the coding complexity is happening on the pre-processing part. Other than that, coding part is simple. Then interpretation is going to be important, and also before the training the model, picking up which features should go into the model, that also becomes very, very important. So I'm going to use Scikit-Learn. So if you guys can open this file in your using your Jupyter notebook. If not, again, let me quickly remind you guys. Somehow I cannot see the. So if you just search Google Colab, for those who don't have Jupyter notebook, Google Colab, just go to Colab, and this is what I had earlier. So I'm just going to cancel. This is what you're gonna see. And then from here, choose upload the notebook that you want to work with. For that, you need to go to the folder that I shared with you. And this is the folder that I shared with you. So upload it. So today, I don't have any data set to share with you. So we are just going to use some data set from Scikit-Learn. But otherwise, if we had a data set, remember for that data set, you need to upload that data set for this session as well. Maybe next time on Saturday, so we're going to use this part again. But for today, we don't need this part. You're just going to just follow me as I type the code. So if you don't have Jupyter Notebook, you can use Google Colab. But let me go back to Jupyter Notebook. All right, so let's just run this part. This is just importing NumPy, which is a library that we can use to work with arrays, and importing matplotlib, which is, again, another library that will help us plot nice graphs, okay? And I'm going to import some of the, normally, I import each of the modules or libraries that I'm gonna be using whenever I need them. And then later on, when I put things together, I move things to the upfront so that I have all the libraries that I'm importing for that project. So, but I just want to show you that we are importing the classes that we're going to be using to train a linear regression model. So from Scikit-Learn's linear model module, okay, we are going to import linear regression. Okay, so for now, linear regression. Later on, we're going to import more, more classes. Okay, so let's import linear regression. So I talked about this last time. I'm just going to use a data set which is available from Scikit-Learn. You can find this data set so many places. It's just an ABC of machine learning algorithms, Boston data set, right? So from Scikit-Learn, I'm going to import the function to import this data set, load Boston. This is the Boston data set. This is the function or method that I'll be using to import this data set. So let's call this Boston is load Boston. So the moment I do this, I'm going to have this Boston data set, which comes with the data, the target variable, the description, the columns of the data set. So it's like a dictionary. So Boston. Look at how Boston. So the Boston data set it's like a dictionary, as I said. It comes with data, target. The target is the house price in our case. Feature names, it's the columns of the data, the names, and then description for the data set. Okay. So what I'm gonna do is I'm going to assign X to data and Y to target. So let me use capital X is Boston.data and Boston dot okay. So data is assigned to X, which is capital X, which is representing my feature set, and target is assigned to Y, which is representing my target variable. Okay, so let's see. Remember, one of the first things we do is let's see how many data points we have, how many features we have. Let's call the shape method. And I have 506 data points and 13 features. So this Boston data set is actually giving us the average of room numbers, the average of house prices for houses in the towns in Boston. Okay, so there are 13 features in my data set. Now I want to, before doing anything on this data set, I would like to create scatter plots of my features versus my target variable, just to see how my target variable is related to my features. So I can do a lot of things with this information. I wish I had more time to talk about this, but at least let us just see how my features individually look like with respect to the target variable. Again, target variable is median house price in each town. So for that, I'm going to, so I have 13 features. I'm gonna have create 13 figures. Each figure represents scatter plot of one feature versus the target variable. That's what I'm gonna do. So there are different ways of doing that. I just want to create, I just want to show you how to create such figures using for loop. That's all. Okay. So, but you can do this in many different ways. And I'm not an expert of creating those figures, but I find it, I mean, useful to learn about these kind of things because, I mean, you may not find these kind of things specifically, you know, taught or talked about in different places. Okay, so what I'm gonna do is, let me first show you this. I can create subfigures. Okay, let's do this. So this, in a moment, you will see what fig means, what axis means. So I'm going to create PLT. PLT is the abbreviation I'm using for PyPlot, matplotlib.pyplot. So I'm going to create a subplot, which is 2 by 2. So I'm going to have 4 figures, but it's going to be in a grid of 2 by 2. Okay. And I can also assign adjust the figure size. Okay, let's make this 8 by 3 inches. Okay, and I mean you can do let's do this much now for now. So as you see, I have 4 figures. Okay, 4 figures, 2 by 2. So I have y-axis and an x-axis for each figure. So this creates some, it doesn't look really nice. So there are so many things that you can control. Okay, there are so many things. So what I'm going to do is I'm going to say share x true and share y true. So when I do this, my figure is going to look better because all these figures are going to have, so these 2 will have the same x values, those 2 will, so 0.2 corresponds to exactly the same points on these 2 figures, as well as 0.5 on the y-axis will correspond to exactly the same point. So I just removed clutter in the data. Okay, so here figure is this fig, F-I-G, is referring to this entire figure. Axis is referring to each of these figures. Axis is actually holding 4 objects, and each object is referring to one of these subplots. So if you want to see how axis looks like, I'm going to print it so that you can see it. Print. Okay, as you see, axis is actually so here it is it is referring to 4 figures. It's actually just following this figure. So this axis subplot, this object is referring to this first figure. This guy is referring to the second figure. So 1, 1, 1, 2, 2, 1, 2, 2. Well, if you like, you can actually turn this 2 by 2 matrix into a 4 by 1 vector by using Ravel. Okay. Now, as you see, that 2 by 2 matrix is turned into, in this case, 1 by 4 vector. So why did I talk about this? Because when you create for loops, this might come in handy. So that's also, you don't have to use it, but it may come in handy. Okay, so let's continue. So this is just an introduction to what we're gonna do. Now I'm going to create a figure for each feature and median house price for each feature and median house price. All right. So I know that I have 13 features. So what I'm gonna do is I'm gonna create a subplot with 3 by 5. Okay, that's what I'm gonna do. So let's do it. Fig and axis is actually subplots. Okay, PLT, don't forget PLT. 3 by 5, and I will use figure size. And how do you know this is the good number? So you can use different numbers, but I just prefer using this for now. Okay. equals. Okay, so this is how the figure is going to look like. So I created 15 figures. All right. Now I'm going to go through each figure. In each figure, I'm going to plot a feature and room price. Okay, room number. I'm sorry, a feature and median house price. Okay. So for that, I'm going to create a for loop. So my for loop is going to be looping over features as well as the figures. So I will be referring to features. So I have 13 features. AX will be referring to each of these figures. So AX equals 0 will be this figure. AX equals 1 will be referring to this figure. Okay. So my for loop is taking in I and AX. I have two indices. So in I and AX in. So I'm going to enumerate. You know, when you enumerate, I will be referring to the number, and the AX will be referring to the objects, right? Enumerate. I'm going to take a axis. My axis. This is the axis. The axis is right now 3 by 5 matrix, but I'm going to label it. Okay. So you know what this means. AX that labels is going to create a vector of 15 members, and I will be the index of the first member. AX will be the object itself. Okay. All right. This is my for loop, and inside the loop, if I is greater than 12, because I have 15 figures but 13 features, I begins from 0. If I is 12, this is going to be the last feature. I equals 12 means the 13th figure. So I don't want to show this and this guy, because these guys, I don't have any feature to show. So if I is greater than 12, what I'm going to do is, for that I, AX, which is referring to individual figures, that AX for that I'm going to set it invisible. Okay, set visible false. Okay, so let's do this. So as you see, those two guys are disappearing. Okay, so I have 13 figures, and each figure will be representing one feature. Okay, if I is greater than 12, make it invisible. And then just, you know, if that is not the case, just continue. Okay. All right. Now I'm going to work on each of these figures. Again, each figure is represented by AX. AX is taking from this list of objects. AX equals 0. I equals 0 refers to this first AX. Okay, so I'm going to take each of these AX, and then I'm just going to plot. For that, in that AX, I'm going to plot the first feature. So what is this X? Let me remember. X is my data set. Sorry, guys. This is my data set. So when I say X, this, okay, I'm referring to the first column of my data set. This is the first column of my data set. 506 numbers, the first column. If I refer to this is the second column of my data set. Okay, so what is happening here is I'm referring to the ith column of my data set. I'm plotting the ith column of my features. If I is 0, I'm plotting the first feature. So what is the first feature? Where is it? Feature names. So these are the feature names. The first column is referring to crime rate in the population. The second column is some measured chemical in the air of per meter cube. I don't know. I don't remember exact. So this is number of this is the square footage of industrial area in that zip code. So each of these are features about that town. Okay, telling something about that town. This is the number of rooms, average number of rooms. So number of rooms equals 3 houses. in that what is that in that town. Okay, this is the average age of the houses in that town. So each of these are referring to a certain feature of houses in that town. And when I is 0, I'm referring to the first one. When I is 1, I'm referring to the second one. Okay, I'm plotting crime versus median house price. So let's do it. This versus Y. So this is referring to the ith column of my feature set. Y, remember, is my median house price. Y is my median house price. Where did I do that? Here. Y is the house price. Target is the house price. Okay, so if I do that, so let's see what's going to happen. So it's a meaningless figure because it is plotting a line plot here. So I don't want a line plot. So what I want is each data point should be represented by a circle. Okay, so when I do that, now it looks much better, right? So here, this is the first feature versus the house price. This is the second feature versus house price, and so on and so forth. So let's make this a little bit nicer. So when you say alpha equals 0.5, this controls the intensity of the color. So you want the things be, so if the number is really big, it's going to be darker. If the number is small, it's going to be lighter. Okay, so let's continue. Let's do a little bit more on this. I also want to put the name of the feature on top of each figure. So if this is the first feature, I want CRIM appear on top of the first feature, so on and so forth. So that's what I'm going to do. AX set the title. Again, remember, AX is referring to each of these figures. AX is taking values from this list. So set title of this. What is the title? So this is now what this is a placeholder. This is the placeholder format. Okay, you know this from, I think from Python, right? So whatever the I value is will be inserted here. This is a placeholder. If I is 0, I'm going to be plotting 0 here. If I is 1, I'm going to plotting 1. Let's see what happens. So 0, 1, 2. Okay, this is the order of the features. This is 0th feature. This is the first feature, second feature. I also want to plot the name of the feature. So I can do that. Let's put a column here. Okay, and another placeholder. This second placeholder, the first one is for I. The second placeholder is for the Boston feature. Remember here, Boston feature names. It's a list. So if you say Boston feature names, it's an array actually. Boston feature names 0. If you say that, it's referring to the first feature. If Boston feature names 1, it's referring to the second feature. If you say 0 to 1, actually, so you are referring to the first and the second. The third is not printed actually, right? So this is Boston feature names. So Boston feature names, but I will be plotting the ith feature. If I is 0, I'm referring to the first one. If I is 1, I'm referring to the second one. So let's see what's happening. What's going to happen? Okay, 0. This is the first feature, second feature. I spent so much time on this, right? So let me finalize this with setting the Y label. AX set Y label, and this is the median house price. Okay, I think we are done. All right, so what? Why did we take this long, painful process, right? So I hope you got this one. You can use this for any other project, and then I strongly recommend before you begin working on the data set, please create a scatter plot. There are many different ways of doing this, easy ways of doing that, but being able to control each feature and each figure is nice. So you can do, for example, for continuous features, you can create a scatter plot. For categorical features, you can create a histogram. So if you are able to control each figure individually, you can create really nice combinations of figures. So, okay, why did we go through this painful process? First of all, if you look at room, right? This is room number. So as room number is increasing, median house price is increasing. It's almost like a linear relationship here, right? So as room number is increasing, median house price is okay. So this is, this is the socioeconomic, what is that, level of the average population in that town. So if this is going down, this indicator is going down, the house price is going down. And as you see, it is not a nice linear relationship, it's actually a non-linear relationship. Non-linear means you cannot, so a linear line is not going to actually, a straight line is not going to give you the best representation of this relationship. It should be a curve. That's why I call this non-linear. So why did we talk about this linear and non-linear? Maybe later on we're going to talk more about this if we have more opportunities for these workshops. If it is a linear relationship, I can simply include into my linear regression model, I can just include room as it is. If there is a non-linear relationship, it is not enough to just include this variable itself. If I just include this variable itself, what I'm getting is actually a straight line going through this data point. I should include, in this case, I'm just making an assumption now, in this case, in addition to the variable itself, I should also include the squared of this variable. Okay, so you can include the cubed of this variable too, but I wouldn't go that far. So I think most of the time, just squared will be enough. Why? This variable plus LSTAT squared together is going to help you to capture this nonlinearity. So we call that polynomial features. So this is the feature itself. The squared of this feature is the polynomial feature. Okay, the polynomial of this feature. Okay, so you might see some of the, look at this. This basically tells you that whatever this variable is, it's a categorical variable. It's a categorical value. There are only two possible values, 0 or 1, right? There are only two possible values. All right. So there are some variables that again that are taking values. So this one is taking values from a smaller set of values. You can treat this as continuous or discrete. So there is really not a very clear line in between continuous and discrete in this case. Okay, so look at here, this one, it also tells you that there is some nonlinearity here. And there might be, for both cases, there might be some outliers as well. All right, so I think this is enough for this part, and then let me check the time. So let's continue. Let's split our data into training and test. Okay, let's split our data into training and test. And oh, I didn't see the, sorry, I didn't see what you posted on the chat. Target variable or target variable? It's target variable. Okay. And Roberto, thank you so much for posting the explanations on what each feature is. Thank you. And Natana says this is so great. Thank you for posting it, Roberto. Okay, so let's split the data into train and test. So for that, from Scikit-Learn, okay, I'm going to remember from last Saturday, if you were here, I'm going to use model selection. Okay, and I will use train test splits class, okay, which will help me to split this data into train and test, and then let's do it. So you can name it anything you like, but the first data is going to be, sorry, I missed the first two inputs with import method. Can someone, let me post it quickly. Okay, so X-train is a train data set, and then I have the test data set. I call it X-test. You can name it anything, okay? Something that will indicate that it's trained data set, it is test data set. This is the train labels, which is corresponding to the features of the train data set, and this is the label corresponding to the test data set. And I'm going to train test splits my X and Y. Okay, this splitting occurs by randomly splitting it. First, you shuffle the data set, and then you split the data set. Okay, random shuffling, and I use the word random. Okay, so if you are curious about how computers generate random numbers, please go ahead and Google it and then read it. But computers generate random numbers by following certain sequences. let's say we are running some experiments. Let's say we want to test the performance of a model on this data set, and you and I are working on this model, and we want to get the same split of data, same random split. How can same random, right? It's two controversial words, same and random. We can do that by setting the seed, random seed, to a certain value. So random state equals, let's say, 3, means all of us, in this case, will be using the same random sequence of random numbers. So in other words, I expect all of us have more or less the same split, not more or less, same split of data set. Okay, now we just split our data into train and test. Now it is time for us to train the model. For training the model, I need to have my linear regression class available, imported already. Let me check one more time if I did that. Yes. So I imported linear regression from Scikit-Learn. By the way, this is not the only library available. There are different libraries available which will allow you to do linear regression. I prefer using Scikit-Learn. Okay, so let's do it. Now I'm going to first instantiate my linear regression model. Let me call my model as LR, linear regression model. So you can call it anything. My LR, your LR, you can call it any name you wish. Okay, LR. And this is how I regression. Okay. This is how I instantiate my model. The moment I do this, whatever linear regression, whatever methods and attributes linear regression comes with, LR inherits them. So LR is an instantiated object from linear regression class. Okay. Okay. So let me run this. Any machine learning model comes with 3 basic attributes. Okay. Fit attribute. Not attribute, methods. Fit method, and then what is that? Score method. Okay, fit method and then score method. What the third one? What was the third one? Fit and score. Somehow I forgot the third one. I'll remember in a moment. So the fit method is going to help us, and predict method. I'm sorry here now. So fit method is going to help us train the model. Score method will help us to get evaluate the model actually, and predict will help us to predict using the trained model. The trained model will help us to make a prediction for a new data point. Okay, so these are the 3 basic. What is that? Let me change this to 3 basic methods that we are going to be using for any coming with any machine learning model. Okay, so now let's take LR, and I'm going to first fit. Okay, remember LR is my model, which comes with all these attributes and methods, and fit, score, predict comes with LR. So LR.fit is going to help me train this LR model using my trained data set. Don't forget, okay, this is a supervised model. For supervised model, you not only have the attributes or features, which is X-train, you also need to put in the target variable, which is Y-train. So the moment you say LR.fit X-train, Y-train, your model is trained. That's it. Your model is trained. Now, what you have to do is you can test your model. First of all, let's see how our model was doing on our trained data set. So again, LR, the moment I say LR, LR is a trained model now. So I'm going to take LR score. What is the... So when you say score, what it's going to do is LR is going to first predict. So it's going to, let me... So LR.predict, okay. So this, I'm sorry. This will give you this will give you the predicted values for your trained data set. When you say lr.predict, it is going to give you the predictions for all the data points, in your trained data set. Next, I'm describing what score does. It takes this trained model, this predicted values, and then what it does is it simply finds this r squared. Okay, 1 minus. Remember what r squared was? You're going to sum from I to n, right? And this is the this is yi minus that's y, right? Right. And the next one is sum yi minus. Sorry, guys, just 1 minute. Why? Let me see. Yeah. Let me take the squared and let me also take the squared. Okay, so this is what it does, right? When we take L score. So let me also LR dot score. Okay, so it first predicts y hat, and then it performs this operation on y hat. So that finds your r squared. So this is nothing but the r squared. This one is nothing but the r squared. Okay, now let's find the okay, let's find the score. Okay, guys, this is the score, 0.72. This is the r squared on my trained data set. So you can print this nicely. Sorry. And here, okay, hopefully it's yeah. So this is a placeholder for the score, and then I'm only printing the 2 decimal digits. Okay, so that just to make things look more beautiful. So this is my score on the trained data set. If you wonder what is my score on the test data set for this model, all you have to do is, let's take this guy and go to the next line. And this is going to be my test data set. And again, the rest is very simple, right? So instead of train, but you need to know what you're doing, right? That's it. So my test data set score is better, 0.77 than my trained data set. So my test data set is better than my trained data set. Interesting. Okay, so I think I'm almost up to the time. And for ridge regression, everything is very similar. And let me just show you how you can do ridge regression, and then I'm just going to stop there. Okay. So for ridge regression, you need to go back here, and let me just copy this part. So it's again linear model, but this time it is ridge. Just say ridge. Okay. So we imported the ridge regression, and the rest is the same. So let's just copy. And I hate doing this, guys, so I prefer typing it, but for the sake of, let's say ridge. Okay, so this is L ridge, and the rest is just the same, guys. Just copy. Okay, let's call this ridge. So don't forget to use the same names. And let's see if ridge regression is going to give us any different value on the train set using rich and on rich. Okay. Yeah, it gave the same result. By the way, if you wonder what happened here, so rich, remember rich has this alpha value, right? So remember this, loss plus alpha. I'm just going to write W. Where's this? Let me use this way. Right? Remember this, loss plus alpha times W. So this part is the penalty term. So with ridge regression, I introduced a penalty term, but I didn't indicate any alpha value. Actually, as of now, my ridge regression is taking the, what is that? The default alpha value. So I can say alpha is 100. As you see, my performance has changed. When alpha is 100, I'm putting a lot of weight on the what is that? On the penalty term. So let's try one thing, okay? Let's try one thing, and I'll stop then. So let's also look at the test score. Okay, 70 versus 72. Okay, I'm changing my penalty alpha to 10, 72 versus 75. So this alpha term is impacting my overall loss. So that's why we need to search for the best alpha value. That's why I said it is an important job for you guys when you train your models to find the best hyperparameter value. So alpha is called a hyperparameter value. Okay, maybe next time we can talk about how we can make a search on this hyperparameter value. That is called, we call this grid search, okay? So the simplest way you can do is you can create a for loop and then change alpha from 0 to some large number and then record the scores for each alpha. So you have to retrain the model for each alpha value and record the score and then compare which of the score is the maximum, find the maximum score which corresponds to which whatever the alpha value is, that alpha is the best hyperparameter value, which gives you the maximum test score, not train, test score. So you can do this running a for loop, but it's unnecessary to go through that process. Again, with Scikit-Learn, we have this nice class called grid search. So we can do this using grid search CV. Again, hopefully, if we have another time, so I can go through how we can make grid search over hyperparameter values. That's an important step in training machine learning algorithms, actually. All right, thank you so much for listening. I'm going to stop here and hope to see you guys in another time. So this Saturday, I will continue working on preprocessing. So if you can stop by, it's going to be between 9 and 11 Pacific time. Other than that, take care, guys. Okay, thank you for listening. Bye.